Okay, so hi everyone, my name is Shanji from UNSW Canberra, and this is our paper enhancing security in third-party library reuse, like detecting one-day vulnerabilities through code patch analysis. So nowadays, we can see that most of the softwares have many different functionalities, and it makes it very complicated for developers to maintain and update the software. So many developers will choose to use code reusing for their software build. And the current approach for code reusing might look like this. So firstly, the library developer will put their open source libraries to public platforms like GitHub or maybe GitLab. And if the library user would like to reuse it, they will carry out a process called third-party library reuse. For briefly, third-party library will be referred to as TPLs in the following. And with third-party library reuse, we will have a software with library reused. But what if there is a vulnerability inside of the open source library? Traditional way of patching is the library developer will build a patch and also put it on the online platform, and the library user will try to collect the patch and apply these patches to their software so that their software will be protected. A one-day vulnerability might be propagated to the downstream software if it is not properly patched. For example, here is a React OS. So this software actually reuses a lot of different libraries. For example, zlab, freetab, and maybe labjpeg. And there's a vulnerability named CV 2018-14498 in labjpeg. So if React OS developer didn't patch this vulnerability properly, this CVE will not only affect labjpeg, but also affect React OS. So it sounds like this process is pretty simple, but when the code base grows, several challenges will occur. So firstly, large-scale patch collection requires significant amount of human efforts. And secondly, libraries may also nestedly reuse other libraries. For example, React OS reused freetab, and actually freetab itself reused libbzip2. And this means React OS actually reused libbzip2, but the developer of React OS didn't realize that. So, and then the third challenge is that it will be hard to determine if there is a vulnerability inside of software if there are some custom modifications of the library. These three challenges lead to three research questions. So the first one is how to build a database to effectively support one-day vulnerability detection. And the second one is how to identify reused TPLs in the target program. And the third one is how to accurately identify one-day vulnerabilities, even with custom modifications. Based on our manual analysis, we have three observations. So for the first one, for the database, a super database for one-day vulnerability detection should be comprehensive, specific, and maintainable, and LLMs can minimize the manual efforts for data collection. And for the third-party library reuse detection, our observation is that TPL reuses can be identified through code similarity comparison, and sufficient and accurate TPL information can optimize the process of detection. And for one-day vulnerability detection, our observation is that one-day vulnerability can be identified through patch analysis, and for example, semantic information should also be used to enhance the detection process. There are many previous works focusing on this area. Their name might be maybe supply chain security or maybe third-party library security, and most of them can be categorized into two groups. The first group is license-based detection, and the second group is code-based detection, but most of them suffer from many limitations, like the license-based detections suffer from high false negative rate due to the poorly maintained licenses by software developers, and the code-based detection might suffer from high false positive because there are many custom modifications. To fill this gap, we developed our new tool, Vulture. It is an accurate one-day vulnerability detector. Okay, so this is a overview and the workflow of Vulture. It is actually composed of three components. The first one is TPL filter construction. It will build a database to support further analysis. And the second component is TPL reuse identification. It will generate a reuse report to show that which TPL or what TPLs has been reused by the target program. And the third component is one-day vulnerability detection. It will generate a full report containing which one-day vulnerability has affected target program and how to fix it, give some fix suggestions. So let's start with TPL filter construction. So it starts with function summary generation. We will select repositories with more than 100 stars from GitHub and scan the documents with keyword match to exclude non-library repositories. And then we extract each function in the select TPL to calculate hashing value. And as TPLs may nest other TPLs, as we mentioned before, redundant functions might exist in the database. We eliminate these redundant functions according to the function creation time and similarity between functions and TPL name. And this is actually a little bit complex, so we put it in our paper. And after redundant function elimination, we'll have a TPL summary containing maybe fail obstruction, function hashing, burst time, etc. And next, we go to the patch collection. We collect CVE and description from NDSS website and collect all of the commits of CVE affected repos from GitHub. We utilize LLM to identify CVE features and commit attributes, and then use LLM again to map CVEs to commits, and thus extract the patch of each CVE. And we can have a CVE mapping. With CVE mapping and TPL summary, we build our database and to solve the research question 1. And now we have the database. We can go to TPL reuse identification. So we have the target program, and we will generate a function hashing for each function in the target program, and then compare the similarity between each TPL in the database and the target program. TPLs exceeding the similarity threshold will be selected as a candidate reuse TPL, but there are tons of false positives inside of the candidate reuse TPLs if we only use similarity comparison. So we carried out a identification optimization. We compare each candidate TPL with this reused path inside of the target program and keep the earliest created TPL with the most similar name to reused path, removing others. And after that, we can have a reuse report containing reused TPLs, their version, reused files, and reused functions to resolve research question 2. And now we have the reused report. We can go to one vulnerability detection. We firstly, according to the report, we identify candidate one vulnerabilities based on reused TPL and their versions. And we can have candidate one vulnerabilities. For each candidate one vulnerability, we carry out a chunk-based analysis to confirm the existence of the vulnerability. The chunk-based analysis is designed to handle custom modifications, and it extracts semantic information through static patch analysis. To be specific, it groups modified lines in the patch into chunks based on the control and variable dependencies. And it compares targets, vulnerable, and patched code chunks to verify the security patch. Here's an example. This is a patch for CVE 2018 12498. This is actually the official patch, and this one is a patch applied by React OS. We can see that there are some syntax differences, but actually the semantic are the same. So what we do is we firstly group the modified lines into different chunks going to the control and variable dependencies like this, and then we extract the variables operations and how operations are applied to the variable into chunks and generate a abstraction. Then we can compare the abstraction instead of compare the the patch itself, and we can see that, okay, these two patches are identical, and the patch is applied, so no vulnerability is there in React OS. And after chunk-based analysis, we can have a vulnerability report and give some fix suggestions. For evaluation, we designed 2 experiments. The first one is a database quality experiment. We choose 2 academic tools as our baseline. And the second one is scalability evaluation containing benchmark detection and vulnerability detection in the wild. We choose one commercial tool and one academic tool as our baseline. So for database quality experiment, with TPL selection, Vultr excluded non-library repositories and only retain widely used TPLs, thereby reduce storage consumption. And when we try to update the database for maintainability, when we try to add one new TPL, Vultr database is much more compact, making expandation easier and much faster. And for patch collection, Vultr is also much faster than existing tools. And then it's a benchmark vulnerability detection. In 200 test cases, Vultr successfully identified 184 cases, while our baseline only identified 100 of them. For vulnerabilities in the wild, in 5 target programs, Vultr successfully identified 175 vulnerability, while commercial tools only identified 111, and our academic baseline only identified 13 of them. Vultr performed best with its well-designed database and accurate semantic analysis. With comprehensive and specific database, Vultr reduced a lot of false negatives, and false positives are reduced by identification, optimization, and chunk-based analysis. So then for time consumption, Vultr can detect one TPL reuse in 25 seconds and one vulnerability in 5 seconds, much faster than our baselines. So to conclude, Vultr leverages static analysis and LLM to support the whole process of one vulnerability detection, and it reduced false alarms and surpasses existing academic and commercial tools a lot. Okay, so that's all. Yeah, thank you so much.
All right, and if you have a question, please make your way to the microphones. While that's happening, I have a question for you. So you showed a comparison with Snyk, and you showed comparison with other things. Have you reached out to any of the commercial vendors or anybody in the open source community to see if there's any interest in people running this using these techniques?
I think no one is using it right now, but maybe, hopefully in the future, someone will use it. Yeah.
Okay, if you feel like it, in August there's a conference that will be in Hong Kong that's KubeCon, and that will actually be a good opportunity to interact with a lot of those vendors in that space, by the way, if you're curious. I'm not trying to plug like an industry venue here, but I thought it was relevant. Anyone have a follow-on question they'd like to ask? I do have one other. So this necessitates access to source code, as I understand it.
Yes, that's true.
So how effective do you think this would be if you actually had to deal with binaries instead?
I'm not pretty sure. Our next work, we left it for future work. Our next work is for one vulnerability detection in the binary level, but I'm not pretty sure what the performance will be like yet.
Okay. All right. Let's thank the speaker again.
Thank you.